Now, if you notice at the top, I actually gave you two words, mappings and functions, and in fact, they're really, really similar. There's just a tiny difference between the two that would become more clear in a moment. So we'll do functions in a couple of lessons, and it's almost the same as a mapping, but there's a tiny difference. So what is a mapping? So a mapping is a relationship, or well, no, let's take it a different way. A mapping takes an element in one set and returns to you an element or elements in another set. So that's a very long definition, but really it comes down to this. A mapping takes one thing from one set and gives you usually another thing from another set. So it's a relationship between two lists of numbers. So like a simple example, you can draw these on graph like here. So here is the set with elements A, B, C, and here's the set with elements 1, 2, 3, and this is our mapping. If you give it A, it gives you 2. If you give it B, it gives you 1. And if you give it C, it gives you 3. Or, maybe to make it look more familiar, you can say f of A equals 2, f of B equals 1, and then f of C is equal to 3. So you can write mappings two ways. You can write it as a diagram or as definitions like this. This is mapping F. You can write it as a diagram like this, or as a list of rules like this. Okay, now there's a little bit of vocabulary. This set here that you begin with is actually called, and it might be a word you're familiar with, the domain. And this set here at the end is called the codomain. So you say your F takes something from the domain and then gives you back something from the codomain. So here domain is ABC, and here codomain is 1, 2, 3. So that's some vocabulary for you. Did you write this down? All of it? Kept writing. Really don't want me to come down there to you. Okay, you got this? Now, the next thing I'm going to show you is very important to explain the difference between a mapping and a function. Okay? So you can do this with a mapping. You could do something weird like this. You could say C goes to 2 and FC equals 2. Now that is weird because now you have two values for C. You could have FC equals 2 or FC equals 3. But that's really weird. You cannot do this with a function. This is not allowed. So if you want, now we can explain what a function is. A function is a mapping that gives one and only one value per input. So this is the key difference between a function and a mapping. With a function, you must only get one value per value you put in. You can't get two values back. So actually, this is interesting because I need to go to the new page. Yes, okay. So if you look here, if I write this, this is actually, technically speaking, not a function. Why not? Because you can have two possible answers, okay? So it's not a function, but it is a mapping. If you want it to be a function, you have to decide if you're going to use a plus or a minus. Now it's a function. So here, this is an example of a mapping, and now this is an example of a function. So, all functions are mappings, but not all mappings are functions. Okay, one more piece of vocabulary and then some examples. So I'll go back and draw a diagram here of a function. So 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, oops, 8, 9. Okay, so 1 goes to 1, 2 goes to 2. No, I don't want 2 to 2, sorry. 2 goes to 4, and 3 goes to 9. Now, what I'm trying to show you here is that sometimes it happens that you don't use all your numbers in your codomain. You see these numbers here? They're not used. They're unused. 1 to 1, 2 to 4, 3 to 9. I didn't use all my numbers here, did I? So we need a new word to describe the numbers you do use, and that's the range. Here we say the range equals 1, 4, 9. And if you want it as a definition, the range is all the values of fx, where x, of course, is in the domain. So to make the range, what you do is you take all your elements in the domain and you put it in your function and see what possible answers you get. And all those answers collected together make the range. So range is basically the collection of the possible answers you could get from your function when you put in different elements from your domain. So the two key words for the first worksheet is domain and range. Domain is the values that go into it, and the range are the values that come out of it. Okay? And then the other two pieces of words are mappings and functions, but today we're just going to look at functions. So it's functions and what are their domains and ranges. So let's have a look at an example. So we'll start off with domain. So my question is, what is the domain of this function? So if I say f of x is minus 9x minus 7, my question is, what values of x can I use? All values of x can go into this, yes? So here, what would the domain equal? Yeah, all real numbers. Because anything can go into this. There's no problem anywhere. This should remind you of semester 1 when we did logs. And there was a question where I asked you, what is the domain of this log? Meaning, what values can you put into the log? What values are you allowed to put into the log? Yeah, well, not 0, more than 0. Let's have a look at another example. I won't write this one down, actually. If the function was quadratic, what would the domain be?
Quadratic?
Yep. Come on.
Anything but the roots?
Nope. Close, but not there. No. No. Anyone else want to try? What is the domain for a quadratic? It's also OR. Can you put any number in a quadratic? Yes, there's no problem. And what about a cubic? Also real. So for linear quadratic cubics, all real numbers can be used. Let's look at an example where that is not the case. So what about this function? Fx equals 1 over 8x minus 16. Now this is different. I cannot put all real numbers into this. What am I excluded from? 2. Why? Yeah, because you don't want this. You don't want this equal to 0. That's a problem. So you can't have x equal to 2. So you could say the domain, there's two ways to write it, equals all real numbers except 2. That's one way to write it. Or another way to write it is minus infinity to 2, but don't include 2, and then 2 to infinity, but again don't include the 2. So go from minus infinity to infinity, but skip the 2. So you can write it both ways. Okay. Let's see what one I'll do now. Difficult one. Yeah, I think I'll do K next. Yeah, K next. Right, so another example now. Fx equals x squared minus 4x minus 12 over x squared minus 5x plus 4. So what could be the problem here?
We have to look at...
Yeah, when the problem could be if this is equal to 0. So if you take out your calculator, you'd see x is 4 or 1 would be a problem, because that would make that 0. So that's no good. So then your answer would just be all real numbers except 1 or 4. Or another way to write it would be minus infinity to 1, 1 to 4, and then 4 to infinity. So you can write them both ways. Okay. One more example of domain. I'm going to do, yeah.
The x for which one?
Oh, where did I get the 4 and the 1 from? Is it?
No, I know it's not
Yeah. So,
3. But for which one?
for this one. Because there's only, because it doesn't matter if the top is 0, that's fine. It's only a problem if the denominator is 0. That's not allowed. Okay. I will do another example. I'll do h there. Okay. Now, we can't use all values of x here. What's the potential problem that we might have?
Negative value
Negative values for what? For the quadratic, yeah. So we should first, we can think about it two ways. We can find what is good or what's bad. So we'll find out what doesn't work. So the problem is if x squared minus 20x plus 100 is less than 0. That's a problem. Okay, if you take out your calculators, I think you get, what are the two roots here? Not 10 and 10, not 20 and 5. Can you do mode 53?
Only 10.
Just 10? Good. So 10 here. 10, not minus 10, right? Yeah. Now what shape is this? A U shape? Yeah. It's a U shape, isn't it? And it's a problem if it's less than 0. When is this less than 0?
Never.
Huh?
Never.
Never. So in fact, this one here, you can use all the values because the quadratic never drops below the x-axis. So in this case here, you can say the domain equals or. Or if you really wanted to be weird about it, you can say it's all the numbers from minus infinity to 10, including 10, and then 10 to infinity. But don't do that. That's how I did it at the back. Don't do that. So it's all real numbers. Now, that doesn't always happen. It just happened in this one. If you were to look at G, for example, the quadratic does dip below the x-axis. So, sorry, not G, U. So in U, you can see you can use minus infinity to 10, but you can't use 10 to 16, and then you can use 16 to infinity. Okay, so I'll do some from question 2, but so I don't forget, I'd like you to try for homework. Yeah, now I'm sorry, it's going to be a lot, and it needs to be a lot because this is a new topic. It's a new topic for everybody, and in the exam it's actually not a bad question. It's one of the questions I recommend you do. So I need N to Z. I need the second half of that done. Now it doesn't take too long to do, okay? It only takes you a few seconds if you think about it. N to Z, the second half, yeah. I don't know about part 2 yet. I'm going to do 2 now. Okay. 2 now. Now, number 2 is finding the range, and finding the range is a lot more difficult than finding the domain. Okay, so please, I'll wait for you. You're all ready to look at this? It's a lot more difficult. So let's look at 2a. Gx equals 6x plus 8. Now, I'll give you a piece of advice. If you're able to visualize the graph, that really helps. And if the graph is always increasing or always decreasing, then the range is equal to OR. But that doesn't always happen. It only happens like in these simple cases. 6x plus 8, could that make any number? Like if I said, for example, I don't know, the number 14. Could you make 6x plus 8 equal to 14?
Yeah.
Yeah, what would you have to make for x? 1. Could you make any number here? Is there any number that could not be made from the formula 6x plus 8?
0.
You could make 0 if you make x equal to minus 8 over 6.
No, it's not possible.
What do you mean it's not possible?
It's not impossible to make.
Yeah, you can make any number. So my advice is, what you do is you write down y equals 6x plus 8. And if you want to make a y, let's pretend y is some particular number. I don't know, like the number 14 or whatever. Can you make any value for y? Yeah, all you have to do is do y minus 8 divided by 6. If you put that in for x, you can make whatever you want it to be for y. So for example, my one at the start was 14. 14 minus 8, 6 divided by 6 is 1. So if I throw 1 into this, it does make 14. So the answer is the range is equal to OR. It's easy to make any number you want here. That's an easy one. Now it gets more difficult. I can go down now? Okay. Now, what about if I had a quadratic? So, function f equals 2x squared minus 4x minus 2. Can a quadratic be any value? What do we think? Can it? So, for example, let's take a very easy quadratic. Y is equal to x squared. Got it? So, what value of x must I use to make y equal to minus 1?
Not possible.
Not possible. Why not?
Because all possible values are above.
Yeah. If I have y equals x squared, what's the smallest number I could make? 0. Could I make any negative numbers? No. So we know straight away that this does not make every real number. Now, it can help if you can picture the graph. What shape is a quadratic? It's a U shape, isn't it? So it can make lots of values for y, but it can't make every value. There's some minimum. So if you look at the y-axis here, it can make all these values for y, but it cannot make these values down here. So the key is figuring out where the minimum is. If only we had some way to find out the minimum of a quadratic. Yes, differentiate and? Not the second derivative yet. Differentiate and? Yeah, so what's the derivative here? 4x minus 4 equal 0. So x equals 1. So x here is 1. But I don't want x, what do I want? Y. So if I put 1 in here, I'll get 2, yeah, minus 4. Now, that graph is not right. It should be down below, but it's not important. The minimum is minus 4. So can we make all values of y? No. We can make all values from minus 4 upwards, but not below minus 4, because minus 4 is the minimum. Okay? So how would you describe the range here? The range equals 4 to infinity. Minus 4 to infinity. Starts at minus 4 and goes up to infinity. You can't make anything below that. The graph doesn't go down that far. Okay, write that down, please. That should be a square bracket in the answer here. Okay.
So, I find that there's no.
Say again?
I find that there's no.
Yeah. Remember, to find a minimum or a maximum, you calculate the derivative and make it equal to 0. And then to confirm if it's a max or a minimum, what do? Second derivative. What's the second derivative here? 4. Is that positive or negative? Positive. Positive represents a minimum. Okay. If it was negative, then it'd be a maximum. The graph would be upside down, and your answer would be minus infinity to minus 4, and you can't make the values above it. Better double check if this is recording. Yes. Okay. Yes. Maximum sound. All right. Another example now. Now it gets much worse. So gx equals minus 2x cubed minus 3x squared plus 9x plus 6. Or if you want, y equals minus 2x cubed minus 3x squared. Oh, well, actually, this is not actually as difficult. It's a lighter one, that is. What about cubic? This one here. What's the situation here? Any ideas? If you picture the graph?
Things get equal to the values.
It is, because what graph is a cubic? Do you remember? It's this shape, isn't it? So if you look at the y-axis, you can get positive, you can get here, you can go down to infinity. The whole y-axis is colored in. There's no minimum on this graph, right? I mean, it's not like the quadratic that it cuts off and you're missing some of your y-axis. The cubic covers the whole y-axis. So cubic, also like linear, nice and easy. The answer is always going to be range equals or again. Okay, another example. So this one now, y equals 1 over 12x plus 12. Can this make any value of y? In other words, can y be anything? Nope. You're thinking of x. X can't be minus 1. But y can perfectly fine being minus 1. So So can y be anything here?
Yeah.
Now let me give you some advice. If you're trying to investigate what y could be, it's sometimes helpful to rewrite it as an equation. So if I just divide this up here, I get 12x plus 12 divided by y, times y equals 1. Okay? Now, if I look at this, maybe this provides some insight. Could y be anything here?
Anything except 0.
Yeah, why can't it be 0? Because you need 1 here. And if you have a number and you multiply it by 0, what do you get? You get 0. Now another way you can think about it is, if I bring the y down to the right, I get 1 over y. So I get 12x plus 12 equals 1 over y. Now again I ask you the question, could y be anything? Y could be anything except 0. So now with just a little bit of rearranging, it can become clear what y is allowed to be and what it cannot be. So here the range would equal minus infinity to 0. Can't use 0 and go back up to infinity. Or in other words, all real numbers except 0. Okay, next one now. And that's a typo. It should say, of course, x squared minus 1x minus 12. Okay, can I continue? Yeah? Okay. So next one. Y equals 1 over x squared minus x minus 12. Okay? This is E, yes. Now, you have two choices here. You could examine it by trying to rewrite the quadratic as two factors, or you could examine it by trying to maybe complete the square. Let's first try factorizing. So what are the factors here? X minus 4